All right, today we're digging into a really fascinating piece of lost history, what you could call the computer that time forgot.
So let's just jump right in with a pretty wild thought. What if our entire digital world, and I'm talking everything from your phone to the massive servers that run our society, was built on a huge mistake? Like a fundamental error in judgment made way back at the very beginning of computing.
You know the deal, right? Our modern world runs on binary. It's all just ones and zeros, on and off. It's the foundation of everything we do digitally. And hey, it's simple, it's reliable, it clearly works. But here's the kicker. Is it actually the best way to do it? Well, if you ask a mathematician, the answer is, surprisingly, no.
And to get why, we need to talk about this weird little number, E. You might remember it from math class, Euler's number. It's roughly 2.718. It's one of those fundamental constants of the universe, kind of like pi. And it turns out it holds this really strange secret about what makes a number system efficient.
Yeah, that secret has a name, Radix economy. It sounds complicated, but just think of it as a way to score how good a number system is at, packing in information. The lower the score, the more efficient it is. And the wild part is that the absolute most efficient, perfect base for a number system isn't a whole number. It's E.
So here's the punchline. If you need to pick a whole number, an integer, to build a computer around, the one that's closest to that perfect E isn't 2, it's 3. Yeah, you heard that right. Mathematically, on paper, a computer built on 3 states, ternary, should be way more efficient than our good old binary.
And look, this wasn't just some theory cooked up in a lab. For a while there, the dream of a 3-state computer was totally real. So let's dive into this almost forgotten chapter of computing history.
Okay, so how would that even work? Well, instead of just on and off, a really clever system called balanced ternary uses 3 states, negative, neutral, and positive. You can think of them as -1, 0, and +1. And the really incredible thing about this is that the system handles negative numbers naturally. No weird programming tricks needed. It's just elegant.
And get this idea is old. Like way back in 1840, a self-taught inventor named Thomas Fowler built a mechanical calculator that ran on this logic, out of wood. Then fast forward over 100 years to 1958, and Soviet scientists built the Setun, the first modern electronic computer running on these same ternary principles.
And Fowler, the guy with the wooden computer, he totally knew he was onto something big. He basically said, look, if we'd all just started counting in base 3 instead of base 10 from the get-go, machines like his would have been everywhere, way earlier. Why? Because the logic was just so very obvious and simple.
And you know what? He was right. That Soviet Setun computer was a seriously impressive machine. They built about 50 of them, and they were cheaper to make and used less power than the binary computers of the day. There's even a story where they replaced one with a binary machine that had the same performance, and the binary one cost 2.5 times more. Just think about that.
Okay, so this brings us to the big question, right? The central mystery. If ternary was so great, so efficient, why isn't everything running on it? Why did binary win? Well, it's a classic story. Practical, gritty engineering versus pure mathematical beauty.
Yeah, let's just put it bluntly. If this ternary thing was so much better, why isn't your phone using it right now?
The answer, it turns out, is pretty down to earth. It really comes down to a few things. First up, simplicity and reliability. A transistor is, at its heart, a simple on-off switch. Making it hold a third state, somewhere in the middle, that's way harder and less reliable. With just on or off, you have a huge margin for error. Then you've got cost. The invention of the transistor made making simple binary parts incredibly cheap. And finally, just plain old momentum. Once the binary train left the station, the entire world built its tracks around.
I saw this quote online that just nails it. To get that same rock-solid reliability with 3 states, you'd have to use a lot more power just to make sure the computer could tell the difference between negative, neutral, and positive. And when you're designing chips, power is everything. So in the real world, binary won because it was actually more power efficient.
And this chart really shows you the bottom line. It compares a theoretical ternary brain for a computer, the ALU, against a modern binary one. And yeah, in its purest form, ternary is simpler. But here's the thing. We've had decades and decades of brilliant engineers finding clever shortcuts and optimizations for binary. So today, binary has a huge real-world advantage in both how much it costs to build and how fast it runs.
But the story doesn't end there, not at all.
Because as we start to hit the absolute physical limits of what we can do with binary, some engineers are looking back at this old, forgotten idea to solve some very, very new problems. You could say we're seeing the beginnings of a ternary comeback. Think about it. For decades, Moore's law meant our computers just kept getting faster and faster, like clockwork, but that's slowing down. And at the exact same time, the amount of energy that things like AI and large language models are gobbling up is just skyrocketing. So the hunt is back on for some radical new ways to be more efficient. And suddenly, ternary computing is looking pretty interesting again.
Which brings us to this really cool project I stumbled upon. A researcher is working on what they're calling a 1.58-bit core for AI models. Now, 1.58 bits, what is that? Well, it's actually a super clever mathematical way of saying it's built on ternary logic.
The project is called Tryon, and the goal is basically to swap out the really complex, power-hungry numbers that AI usually uses with those simple ternary values, -1, 0, and +1. If it works, it could slash the amount of memory and power that AI needs. We're talking about potentially running really powerful AI on simple, everyday hardware.
The creator has this great quote about it. Tryon equals, what if ternary topology itself is trainable? So it's not just about using 3 numbers. The real question is, can an AI learn to use the unique advantages of ternary, especially that super useful 0 state, to make itself more efficient? So, where are we now? Could we actually be on the edge of a whole new chapter in computing? Maybe it's time we started looking beyond our purely binary world.
When you look back, the story of ternary computing is just this classic battle, isn't it? It's beautiful, elegant theory versus messy, real-world problems. And for a long time, the practical solution won out over the pure one.
But here's the thing. Even as binary was conquering the world, a giant in the field, Donald Knuth, he wrote that the special properties of this ternary system might, and I quote, prove to be quite important someday. Well, it's starting to look like someday might be right around the corner.
And that leaves us with one last question to chew on. The future probably isn't about completely throwing out binary and switching everything to ternary. But as the massive demands of things like AI push our current systems to the breaking point, you have to wonder, is the future a hybrid? A world where binary still does most of the work, but we bring in the elegant, efficient logic of ternary to tackle the really tough, power-hungry problems of the future.